All right, let's keep going through uniform circular motion. So when we last left off, we had done example 6.6. So let's start with example 6.7, when we are trying to find the maximum speed to turn a car. So we're told that the max speed with which a 1500, or we want to know what the maximum speed with which a 1500 kilogram car can make a turn around a curve of radius 20 meters on a level unbanked road without sliding. The radius in this case is about what you might expect at a major intersection in a city. Alright, so they've given us a nice list of knowns and unknowns along with a free body diagram. Right, so the free body diagram they've given us is we've got a car, it's experiencing the force of friction, there's a normal force acting on it, and there is the weight of the car. Now we're also given that the mass of the car is 1500 kilograms, that the radius of that turn is 20 meters, and that the coefficient of friction in this case would be 1. And we want to find that max speed. So, if we start by looking at Newton's second law, right, that force is equal to mass times an acceleration. And again, in this case, your acceleration is the centripetal acceleration, which is v squared over r. Now we know this circle, right, this circular path that they're taking is entirely horizontal, which means that your centripetal force, your net force, is not going to be affected by your vertical forces, right? Only your horizontal forces are going to contribute to this horizontal net force, this horizontal centripetal force. And now V here would represent the maximum. So if we find V, we know the maximum speed at which you can make this turn of a certain radius with a certain net force. Now, anything less than that, you would still make the turn, but again, this would be the maximum value that that force of friction could provide given that radius. So, if we expand our equation, force of friction is equal to mv squared over r, right? And the force of friction is the coefficient times the normal force. And again, since this is not a banked turn or anything, your normal force is equal to the gravitational force. Now notice what happens. You can cancel out your mass. So the mass of the car is irrelevant. All that really matters is the radius of the turn and the conditions of the road. The conditions of the road being represented by the coefficient of friction, right? If it's icy, that coefficient would go down. If it's wet, that coefficient would go down. If it's dry, the coefficient would be max. So let's plug in what we got. So 1 times g is equal to unknown v over 20 meters. So let's go ahead and solve that out. And you get a speed of 14 meters per second. So that would be the maximum when the coefficient is 1. And again, it's going to depend entirely on what that coefficient is. Right? So road conditions dictate how fast you can take that turn. Now, keep in mind, there are other ways to increase the speed at which you can turn. So think about, say, racetracks. What's true about racetracks? Well, all of those turns are banked, right? And by banking a turn, you're not just using friction as part of that force that's going to help you to change directions in that circular path. You're also using some component of the weight of the car itself, the normal force acting on the car. So in example 6.8, we've got a curve on a racetrack of radius 70 meters. It's banked at 15-degree angle. We want to know at what speed a car could take this curve without any assistance from friction. So again, they provided us with some nice, helpful images. Um, right, so basically what you've got is you've got yourself an incline, right, that is angled at 15 degrees. We've got ourselves a car on that incline, which has a normal force perpendicular to that incline, and oops, ignore that, a downward force of gravity. Now, keep in mind that when we're looking at this, only the component of your normal force that is in the horizontal is going to contribute to that centripetal force, because essentially what we're looking at is a horizontal circle that this thing is traveling around. So if we kind of just draw it on an axis, so we've got our x-axis and our y-axis. Let me actually use a ruler for that. So we've got ourselves our axes. Now, the normal force in this case looks something like this, right? And your gravitational force looks something like this, right? Where the gravitational force is straight down on your y, and the normal force is going to be at some angle. Now, the road surface, right, is angled like this at 15 degrees. Now, if this is 15 degrees, this is also going to be 15 degrees. So, if we're looking at a horizontal circle where our centripetal force, our net force, is directed in the x-axis, the only component of this normal force that contributes to that centripetal force is the x, or the x component of that normal force, right? This exists in both the x and the y dimensions. So if we're looking at a purely horizontal force here, or net force here, only the horizontal component of your normal force is going to contribute to that, right? The vertical component of it does not exist within this dimension. It doesn't matter. So now if we look at our net force being equal to mass times acceleration, well, our net force in this case is that horizontal component of your normal force, which would be, if this is 15 degrees, opposite hypotenuse, mu mg times the sine of theta is equal to, or sorry, mg times the sine of theta is equal to mv squared over r. Now again, notice your masses cancel out. So what you're looking at is g times the sine of the embankment angle is equal to the max speed over the radius of the circular path. So g times the sine of 15 is equal to your max speed over that 70-meter radius. Right, if we solve that out, again, make sure that you are in degrees and not radians, we get a max speed of 13.3 meters per second. Right, so without the aid of friction, this race car could make it around that embankment going 13.3 meters per second. Now, obviously, if you had a frictional force involved, you would have your net force that includes not just this horizontal component of the normal force, but also the frictional force. All right, so there's a reason you have banked turns in things like NASCAR. Alright, so take a look at example 6.2. We got a block on a string. It spins in a horizontal circle on a frictionless table. Rank in order from largest to smallest. Tensions A through E acting on the blocks A to E. You're given radius, you're given frequency and RPM. Now, if you're given everything in the same units, don't bother converting it because you're just looking at ratios anyways. So pause the video, take a couple minutes, see if you can't figure that out. Alright, if we look at Newton's second law, net force equals mass times acceleration. Keep in mind, in this case, we've got something that is circling horizontally, right, based off of a tension force within a string. So the force of tension is going to be equal to mv squared over r. Now, remember, we were able to determine our velocity as 2 pi r over t, or 2 pi r times frequency. Right, so let's go ahead, and because we're given frequency as one of these variables, let's go ahead and plug in the equation for velocity using frequency as a variable. So mass equals 2 pi r f squared over r. Let's go ahead and continue with this. So 4 pi squared r squared f squared over r. One of these r's can cancel. And we're left with a statement of the force of tension as mass times 4 pi squared rf squared. Now, as we look through scenarios A through E, they're all going to share this in common. So really all we're looking at is looking at rf squared in each one of these scenarios. So for instance, if we look at A, rf squared would be 10 centimeters times 50 RPM squared, which gives us 25,000. So go through and do that for all of the others. Alright, so these are the values you should get. 25,000, 50,000, 200,000, 400,000, 1,600,000. So tension in E would be greater than D, would be greater than C, would be greater than B, would be greater than A. Alright, so in all of these ranking tasks, what you're looking for is some component of variables that you can easily just rank given what they've given you there. And so the last thing we want to cover in today's video is what we call apparent forces in circular motion. So keep in mind there's a term that you guys have probably heard quite a bit, and that is centrifugal force. Now, this is a fake force. It doesn't exist. Now, the problem is 99.9% of people believe that there is a centrifugal force. We even have, medical equipment named after this fake force, the centrifuge. Well, the reason people believe that there is a centrifugal force, and centrifugal comes from the Latin for center fleeing. Right? So centripetal, which we've been dealing with, is center seeking. This means that there's a force that is center fleeing, meaning that if you've got something moving in a circle, people believe that there is some force that is pulling you away from that circular path. But it's a fake force. It doesn't exist. So take, for instance, think about the last time you were on a merry-go-round, and it's spinning really fast. It kind of feels like something's grabbed the back of you and it's trying to pull you off of that merry-go-round, right? Well, that's not the case. The reason people believe that centrifugal force is real is because what they're really experiencing is inertia. Right? So remember, inertia is not a force. It's just a property of matter that says that objects don't want to accelerate. Objects want to keep moving at a straight line at a constant speed. So as you're on that merry-go-round, the reason you feel like you're being pulled back is because your body wants to continue in a straight line at a constant velocity, right? Your body wants to just continue in this path. Unfortunately, the friction, or you holding onto the handlebars of the merry-go-round, is forcing you to accelerate around this circular path. So it's not an actual force that's causing you to feel like you're being pulled backwards. It's just a demonstration that you have mass, therefore you have inertia, therefore you resist acceleration. And a change in direction is an acceleration. Right? So there's a nice little image in the notes with a car going around a curve. Now, let's pretend you're sitting in the passenger seat here. And let's look at two scenarios. One, there's a door on the car. The second, there's not going to be a door. Now, in the first scenario with the door, let's say you're not wearing a seatbelt and your buddy takes that turn real tight. Well, what do? You kind of jam up against the door, right? And why do you continue to go in that circular path? Well, the door is exerting a normal force on you, forcing you to stay within the car. Now, if you're not buckled up and there's no seatbelt, and your buddy takes that tight turn, well, what are you going to do? You're going to continue in a straight line at a constant velocity, and you're going to exit that car. Right? So again, all that centrifugal, let me put force in parentheses, centrifugal forces is a demonstration that you have mass, that you have inertia, that you resist accelerations. Right? So it's not anything that actually exists. Now, the second apparent force that we're going to talk about with circular motion quite a bit is apparent weight. And think back to when we were dealing with forces, right? Your apparent weight was all about the normal force versus the gravitational force. If the normal force you experienced was equal to your actual weight, you feel normal, right? You feel your true weight. But if the normal force was greater than your actual weight, then you feel heavier. And if the normal force is less than your true weight, well, you feel lighter. Now, if the normal force is 0, you feel weightless. Right, so if you need to brush up on that, go back to the, I believe the video is actually called apparent weight, back in the forces unit. But again, the normal force dictates how heavy you feel. Right? It's not how heavy you actually are, but the normal force dictates how you feel. Whether you feel lighter, you feel heavier, you feel weightless. And so let's take a look at, in the notes, there's a nice little roller coaster example there. So they give us a roller coaster and two positions, one at the top, one at the bottom. Now, in both positions, we know that our net force, the centripetal force, points towards the center of the circle. So let's call this position A, and we'll call this position B. Now, at position A, if we look at the free body diagram, well, you're within the loop of a roller coaster, right? So this circle could represent the track. Now, the track is pushing down on you, and you have weight. So in this case, your centripetal force is equal to the combination of your weight and the normal force. Now, at the bottom of the coaster, you have a normal force, and you have weight. So your centripetal force is the combo of your normal force and your gravitational force. Now notice, in this case, in position B, your net force is an upward net force, right? Which means that your normal force has to be greater than the gravitational force. Which means that if Fn is greater than mg, at the bottom of this loop, you're going to feel heavier. Are you actually heavier? No. You just feel that way because that normal force is greater. Now, if you look at the top of the loop, your normal force is going to be either equal to or less than your weight, right? So depending on the speed at which you're going, you're either going to feel lighter or you're going to feel your true weight. So that's going to depend entirely on speed. So let's take a look at example 6.9. So a motorcyclist in the Globe of Death rides in a 2.2 radius vertical loop. To keep control of the bike, the rider wants the normal force of his tires at the top of the loop to equal or exceed his and the bike's combined weight. What is the minimum speed at which the rider can take the loop? Alright, so let's start this problem off like we should start off every circular motion problem, and that is with just a general sketch of what's going on and a free body. So at the top of the loop, we have a normal force and we have a gravitational force. Now the radius of this loop is 2.2 meters, and we're told that in order to control the bike, the rider needs to have the normal force either equal or greater than its actual weight. So if we want minimum velocity, then your normal force would equal your weight. Right? That would be the minimum speed at which he would be able to control his bike on that turn. So if we look at our net force here, net force is mass velocity squared over r. So if we're looking at normal force plus gravitational force equal to mv squared over r. And again, these guys are being added because they're both pointing the same direction, right? Both pointing towards the center of the circle. Now in this case, we're looking at Fn being equal to mg. So 2mg is equal to mv squared over r. Cancel out your masses, and you have 2g is equal to v squared over r. Or 2g is equal to v squared over 2.2 meters. So go ahead, solve out for v. And we get an answer of 6.57 meters per second. Again, notice your masses cancel out. It doesn't matter about the mass of the motorcyclist or the rider. All that matters is the speed at which you're going. So anything greater than 6.57 meters per second, he'd be able to maintain control of his bike. Now in example 610, we've got an 18 centimeter diameter ultracentrifuge. It produces an extraordinarily large centripetal acceleration of 250,000 g, where g is the free fall acceleration due to gravity. What is its frequency in RPM? What is the apparent weight of a sample with a mass of 0.003 kilograms? Alright, so let's start just by setting this up. So the diameter is 18 centimeters, so radius is 9 centimeters, right, or 0.09 meters. We know the acceleration is 250,000 times acceleration due to gravity. And we want frequency, and we want apparent weight. So if we're looking for apparent weight, we're looking for the normal force. Alright, if we want to find the frequency, we are going to want to know the speed. Alright, so acceleration is v squared over r. So 250,000 times 9.8 is equal to v squared over 0.09 meters. So the speed comes out to 469.6 meters per second. Now again, speed is equal to 2 pi radius times frequency. So frequency would be equal to v over 2 pi r, or 469.6 over 2 pi times 0.09. So go ahead, solve that out. And we get a frequency of 830.4 hertz. Now they want it in RPM. So hertz, keep in mind, is revolutions per second. So 60 seconds for 1 minute. Just do a little DA. And you get 49,823. 823 revolutions per minute. And so now if we want to find the apparent weight of this sample, well, the apparent weight is your normal force. So let's say this is an overhead view of our centrifuge. And this is your sample. Well, the only thing that is acting in the horizontal is the normal force of the test tube itself pushing on the sample. So if we're looking at net force equal to mv squared over r, and a good other way to think about the centrifuge is think about that carnival ride where you guys walk into that room, you step up against the wall, and it starts to spin, and then the floor drops. Well, what's the reason you're spinning in that circle? Well, it's the normal force, just like the centrifuge. So our normal force is equal to mass times v squared over r. So your normal force is equal to 0.003 kilograms, 469.6 times 469.6 meters per second squared, and all of that over 0.09 meters. So the apparent weight, the normal force, comes out to 7,360 newtons. And so the last thing we want to look at is Stop to Think 6.3. So in Stop to 6.6.3, they have a car on top of a hill. You've got a normal force, you've got a gravitational force, and you want to determine whether the normal force is greater than the weight, less than the weight, or equal to the weight. Or whether you don't have enough information knowing the speed at the top of the hill here. So take a second, pause the video, think about the answer there. Alright, well, easiest way to look at this. Alright, fill in the rest of the circle in your mind. Now, we know that the net force always points towards the center of the circle. So we know that we have a downwards net force, a downward centripetal force. So if your centripetal force is downwards, your net force is downwards, your downward force has to be greater than your upward force. So in this case, your normal force is going to be less than the weight of the car and its occupants. So we're going to stop there today. I'm going to be uploading some problems that deal with dynamics in circular motion, as well as a daily problem that will deal with a scenario similar to what we've seen today. So keep an eye out for that. Hope you all are doing well, and I will see y'all soon.